This video is on the average rate of change. I'm going to be using my writing color plus 3 additional colors as an FYI if you want to go grab 3 colors to use real quickly, or you can just use your pen or pencil. When a function is linear, the rate of change is, and the word that should be popping in your head is constant. And constant rate of change should also be causing a second word to pop in your head, which is hopefully slope. So when a function is linear, the rate of change is constant and is called the slope. When you read or write the word slope, it is implying a constant rate of change and a linear function, so we cannot use the word slope as a synonym for the common ratio in exponential functions. I saw a few students doing that in our last unit. We just want to be very careful with that vocabulary. Other functions also have a rate of change. They won't be constant if they're not linear, and we can calculate the average rate of change. This calculation will work for linear functions as well. It will work for all of our functions. We just won't call it slope. I'm going to write it in words first, and then I'll put the mathematical notation. It is a ratio. In the numerator, we're going to have the net change in y values. And then we will divide it by the length of the x interval. So the net change in y values over the length of the x interval. And I made a very specific choice here. I could have written the net change in y values over the net change in x values. We're going to be using interval notation where we're given 2 x coordinates. So I believe this wording will just help us keep everything a little bit more organized. And then in symbols, I'm going to write this symbol. It's a Greek letter delta. So delta y over delta x. This is the notation I used when I taught 8th grade math to talk about slope. Your teacher might have used a different notation. In fact, I'm going to write that right now, but please, you don't need to write this down on your paper. I just in case you're used to seeing it. So your teacher might have done y sub 2, which is a y coordinate, subtract y sub 1, and then divided that by x sub 2. Minus x sub 1. That notation is absolutely correct. It ultimately does the same thing as delta y and delta x. I personally like using this notation. I think it's a little cleaner, and I'll show you why here in a little bit. So if this is new to you, I'm just going to write that symbol is delta, and it means change in. Put little quotation marks around change in. And now let's do some examples. We have a graph that is comprised of 3 different linear pieces, but it isn't linear on its entire domain. So it isn't one continuous straight line. Our directions say to find the average rate of change over the interval 0, 4. It is a closed interval. The domain of this function is negative infinity, so negative infinity to 4. We're not going to worry about this other part of the graph since it tells us just to look at the interval from 0 to 4. It does say interval. Unless we're talking about range, I just want you to have in your brain that we are always going to be talking about x coordinates. So unless we're talking about range, assume that the numbers in the interval are x coordinates. So this tells us that we're going to start looking at our graph when our x-coordinate is 0, and we're going to go until our x-coordinate is 4. Our graph is increasing until we get to an x value of 2, and then it remains constant. There's no change at all. However, we're looking at what's happening on average over this entire interval. So ultimately what we're doing is we have a starting point, an ending point, and we are connecting these with a straight line segment. And we are going to calculate the slope of that line segment, not the function itself, since our function isn't linear, but the slope of this line. I am going to write out what the coordinates of these points are, and we're going to put them into a table. So our first one is 0, 0. The coordinates of our second point is 4, 3. I'm just going to make a simple table. X, Y. It actually does not matter which point I put in my table first, just as a heads up. I'm going to put the left point in first, the start. So 0, 0. And when I say start, I'm talking about the starting of the interval, of course, not the function itself. And 4, 3. Now I'm going to find what is that net change. So I'm going to use my first color, the net change of the y values. So my graph is increasing. How much is it increasing by? And I see that to get from 0 to 3, I'm adding 3. That's my delta y. So this vertical distance right here is my delta y, which is 3. On a graph, it's nice we can actually see it. I'm having to still use the table because we'll need that skill for when we do some in a little bit where we don't have a graph. And then I'm going to pick my second color for my x values. And now remember, this is the length of my interval. And to get from 0 to 4, I'm adding 4. And that's my delta x. I'm going to use these two values in my calculation, and I always rewrite it. It keeps my thoughts organized. I know what number is going to be in the numerator and the denominator, and it also helps just remind you once you kind of memorize this equation so that you don't accidentally put the y values in the denominator. So we're doing delta y over delta x. I'm going to be consistent since I started using colors. I'm going to see it through. So my y change is 3 divided by my x change, which is 4. Now I can leave this as 3/4, or I can also simplify it to a decimal. So our average rate of change on this interval is 3/4, or 0.75. A decimal is totally cool. If that decimal is between 0 and 1, it means that the length of my x interval is a larger number than the net change of my y value. So my interval is longer than my overall increase of my vertical values. And if it was negative instead, it would mean that my graph is decreasing on that interval. All right, let's try another one. This next one is not made up of any linear pieces, and we're going to do 3 different intervals. So instead of using the pink and the blue like I did above for the x change and the y change, I'm going to use one color for each of these. So this first one I'm going to do in pink. Find the average rate of change over the interval 1, 4. Remember, both of those are x coordinates. So my first x coordinate is 1, and I'm going to go up to the graph until I find that point. Okay, perfection. And then I'm going to find where my x coordinate is y. I go up, I find that point. I'm going to connect these endpoints with a line segment. And we're going to be calculating the slope of that line segment. Now notice our function decreases and then increases, but the net change is a decrease of 1. So we're actually going down 1 full unit in the y values. Let's make a table, put our values in there. So our first point is 1, 5. Our second point is 4, 4. To get from 5 to 4, I'm subtracting 1. So my graph is going down, a net change of -1. And to get from 1 to 4, I'm adding 3. So the length of my x interval is 3. Let's put that into our calculation, into our ratio. -1 over 3. I could honestly just draw a box around that. Since above I rewrote my fraction and then I changed it into a decimal as well, we can do that. Both of these values are mathematically correct. When I'm graphing, I typically use the fraction, and when I'm substituting in values and I'm using this in equation to multiply, I might use the decimal instead, just as a heads up. And since it's negative, that tells me, oh, that this function is decreasing over this interval, which on average it is. The net change is negative. But notice it did decrease, and then increase. Our next interval, new color. So we're kind of starting over. We're ignoring what we did above, basically. Find the average rate of change over the interval from 1 to 5. So that's the closed interval, x interval, from where x is equal to 1 to x is equal to 5. So it's the same starting point, but now x coordinates 5. This, there we go. This is our ending point. We're essentially connecting them with a straight line segment and calculating the slope of that. We have a positive net change, so this will be a positive number when we calculate it. If it's a negative number, we'll have to check our work. We would be very concerned. Even though my graph is decreasing and then increasing. Overall, we increase more than we decrease on this interval. Back to a table. Same starting point, 1, 5, and this point is 5, 7. So we calculate our net change is adding 2. I know above I used this funky symbol. I think just something simpler is a little easier. You can make it look how you like. And then for our interval, the length of that interval is 4, because to get from 1 to 5, I'm adding 4. And now we calculate our average rate of change, 2 divided by 4. So our average rate of change is 1/2, or 0.5. Ooh, yeah, very nice. And for this graph, one more. Find the average rate of change over the interval, the closed interval, from 1 to 6. So what do you know? We're starting in the same place. Our x coordinate is 6, so we're going to go from 1 all the way till we get to 6, coming up to the graph to find that point. I'm connecting them with a straight line segment. We're going to calculate the slope of that, and it is exactly a horizontal line segment, so hopefully a number pops into your head of what this average change might be when we're done. Okay, I ran out of room on my table. It's going to be just fine. XY, same point, 1, 5. This second point is 6, 5. And to get from 5 to 5, my net change is 0. We could write plus 0 if you want to, but like we're adding 0, but technically 0 is not positive or negative. And the length of the interval is 5. I guess to be consistent, I have been writing that we're adding each time what operation we're doing. Delta y over delta x. Those are kind of sloppy looking deltas. 0 over 5, 0 divided by 5, and 0 divided by any number other than 0, of course, is 0. We can rewrite it since we've been rewriting all the other ones. If you wanted to just draw your box around this first 0, that would be absolutely fine. So that's our average rate of change. Even though our function is decreasing and increasing and decreasing again, the net change is 0. When I divvy that out evenly over this interval, the average rate of change is 0. We're going to take a break from the graphs, and we are going to now use 2 points. calculate the slope of the line that passes through the points 6, 5 and 11, 6. We are talking about a line, so that's why I'm able to use the word slope, so it's going to be a constant rate of change. But we're going to calculate the exact same way because it's still an average rate of change. Use my table. Put my coordinates in. It doesn't matter which point I put on top. I usually just use the first one they give me first and then the second one. So 6, 5, but ultimately, since we're doing a ratio, you would calculate the same value. And in fact, you might even want to do it in the opposite order and make sure you get the same ratio as me. I'm going to go ahead and use different colors just to make it look a little cleaner. For the Y change and the X change, I'm going to use the same color just for ease, but I think it will pop just a little bit more. So my net change is we're adding 1 to our Y values, and the length of my interval is 5. So now we calculate that ratio, delta Y over delta X. There, that's good enough, is 1/5. Okay, so our average rate of change is 1/5 or 0.2. Trying to box around it. So my X interval is longer than my net Y change. So we're going over more than we're going up or down. I would recommend trying this next one ultimately on your own. Pause the video, try it, and then play it and see if I get the same thing as you. So hopefully you've done that. So, and I just wanted to point out as well, point. It does say point, which implies that the first number is an X coordinate and the second number is a Y coordinate. When I use the word interval, that's implying that both of those numbers are X coordinates, unless of course I use the word range. And this is really just context and getting used to it. So my net Y change is negative. We're actually subtracting 12. So this function, which is a line, is going down from left to right. And the length of this interval is 4. So negative 12 divided by 4 is exactly the number 3. We could rewrite 3 to the right and draw a box around it just to be consistent. I would be very comfortable just drawing a box around this since I'm not also simplifying it. It's up to you. Also, if you want to use color a little bit differently than how I've been doing it, that's fine too. Now we're going to switch gears. And instead of me giving you 2 points, we now have a function. Calculate the average rate of change over the interval 3 to 5 for the function f of x equals 2 to the x power. So now we have this nice exponential function. We're going to be changing how many times we multiply 2 together. I did not give you 2 nice points to put in the table, which we need to calculate the average rate of change. So we need to substitute in values into the function to find that second coordinate, which we can absolutely do. So I'm going to write us a note so that when you look at this later, which you're supposed to, right? Because these are notes, that you're going to evaluate the function first. So evaluate first. And what I mean by that is we're going to take our function. F of some number, we're plugging in a number, is equal to 2 to some number. And we know exactly what that some number is because 3 is an x coordinate. So we're first going to substitute in 3. So we multiply 2 together 3 times. 2 times 2 times 2 is 8. So when we substitute in 3, we get an output of 8. We can think of that as a y value or a f of x value, but in our point, it's ultimately a y coordinate. So let's be very clear that this will give us the point 3, comma 8. And we're not putting 2 because 2 is our common ratio. Our actual x coordinate came from our interval. It's 3. It's what we substituted in. That's why I think using color there helps it be a little bit more clear. And then we're going to do the exact same thing for the endpoint in this interval, 5. So f of 5, we're going to change our exponent to a 5. Make that look a little bit more like a 5. Oh yeah. 2 to the 5th power is 32. Or the point 532. Now we're able to essentially do what we did up here. Of course, we know this isn't a line, but the process is the same. It's time for a table. I mean, you can use color just to make it pop. To get from 8 to 32, ultimately that net y change is adding 24. And the length of my x interval is 2. Time for our calculation. And that simplifies to 12. So at some point, I'm assuming that since this doesn't have a constant rate of change, I'm going to assume that at some point on this interval, it's growing faster than increasing by 12 and over a next interval of 1. And at some point, it's going a little bit more slowly, and that averages out to a rate of change of 12 on this interval. Okay, same deal on this next one, just a different function. Now I'm giving you a linear function. I would recommend pausing it, going through all the steps again to see if you can do it ultimately on your own. You're going to need to do that in the practice here after this video notes. There we go. So hopefully you've done that. Now I'm going to go through it kind of quickly, as you can tell. So I have 2 x coordinates, that is an interval, x coordinate of 1, x coordinate of 7. I'm going to substitute both of those values into my function. I'm going to set it up first. So I'm first substituting in an x value of 1, and then I'm substituting in an x value of 7. 4 times 1 is 4, plus 1 is 5. So that would be the 0.15. And then 4 times 7 is 28, plus 1 is 29. So this would be the 0.729. Yeah? Do you agree with me? Hopefully. Putting these points into my table. Okay, my net y change is I am increasing by 24. And the length of my x interval is a positive 6. It's 6. Ooh, I'm going to kind of run out of room here. I think I'm going to survive 24 divided by 6. That does simplify to 4. We could draw a box around that 4 just so that it's kind of clear and not cramped. I'm going to rewrite it and draw a box around it. When we have all of these numbers, I highly recommend drawing a box around your answer. And if you're like, hey, wait, that was the slope. Oh, yes, that is not a coincidence. This is a linear function, which means my rate of change has to be constant. So no matter what interval I pick, I absolutely have to calculate a rate of change of 4, which, like we said, is called our slope. So, phew, this is in fact linear. And let's do one more of these. This is a quadratic, which is a 10th grade pattern. Some students see an exponent and they're like, oh, it's exponential. But nuh-uh, it would have to be something like 2 to the x, where we're changing what the exponent is. Instead, in a quadratic, we're always multiplying by that number twice. We're changing what that number is. I would recommend pausing, doing this on your own, and then seeing how you do. Okay, I'm evaluating. the cool thing about function notation is it tells you exactly what number you're substituting in. I'm substituting first in a 2 and then a 6. 2 times itself is 4, so this would be the 0.24. 6 multiplied by itself is 36. This is the 0.636. Time for my table. And the other reason why I like doing this over the y sub 2 minus the y sub 1 is you have to memorize that equation. And for this, is if you're using a table and you know the process, it's a little less memorization. So the net change here is we're adding 32, so our function is increasing from left to right. On this interval at least, maybe not the entire time. And the length of this interval is 4. If you're like, wow, I feel like I've done this a million times now. Well, hopefully now you're super pro and this will just be straightforward. It kind of looks like there's a negative in there. That's just noise. There, that looks a little bit better, which is 8. I could draw a box around it. I'm going to rewrite it just so it's a little bit more clear. So the average rate of change on this interval is 8. If you're like, that doesn't really seem like a rate of change, it's technically 8 over 1. So it's saying on this interval, for each x value I move to the right 1, my graph on average is increasing by 8. That's ultimately what it's saying. And then finally, here's a table. I'm only giving you one because we've actually been doing a table on every single one of these without me starting with a table. So I would try this on your own, and you should be super pro. Find the average rate of change over the interval 2 to 4, both x coordinates, for the function shown in the table. If you look at this function, you can absolutely find a pattern and you could continue it on, but it is not linear, just as a heads up. So we care about our x coordinates being 2 and 4. So to get from 2 to 4, the length of that interval is 2. And then I don't care really what's happening there. I care that I'm going from 12 to 19. That net change is that we're adding 7. And now we're ready to do, just like we have on every single one, delta y over delta x. 7 over 2. We can leave it as this ratio. We can also turn it into a decimal. We're cool with that. That kind of looks like a repeating. That's just sometimes I write messy 5s. And that is the average rate of change on this interval. Now, since this is not a constant rate of change, if we made our interval shorter or longer, then our rate of change would be different, just as a heads up. So it does depend on what interval we have chosen. Hey, nice job. Ask your teachers if you have, if you have any questions at this point.